axioms for positive reals. There's just several little details remain to be done, and then we'll be all done. So the first step is our step 6, which is verifying. I'll just write down what we're doing, and then I'm going to have to back up a little bit. But so we are verifying that the axioms of multiplication and distributivity hold for all R, right? Last time we did it for the positives. Now that we have the positives, we just need to extend it to the negatives, and then we'll be done with multiplication. So before we prove that, there's several things that we're going to need that we've used before, but I'm going to teach you a vocabulary word first. This is really great. The plural of lemma is lemmata. So we have several lemmata to go through in order to verify this. And it's stuff that we've all seen before. It's stuff that we already know, but I'm just repeating it here to keep it. These are the things that we're going to rely on from what we've done before. So we're going to need 114a, which is the cancellation law. That says that if x plus y equals x plus z, then y equals z. This comes for free with the addition axioms. We proved all of these. These were additional properties that we proved after we showed the original addition axioms. So we've already shown this for addition axioms. So now that we've proven that the addition axioms hold for our cuts, then this stuff holds also. So 114c is that if x plus y equals 0, then x equals minus y. And then finally, the one that we're really using is D, which says that gamma equals the inverse of gamma. Then we also need, I finally figured out why Rudin put part of the ordering before the multiplication, because we're going to need the first part of the ordering. So 1.17i is that if alpha, beta, and gamma are elements of R, then, and beta is less than gamma, then alpha plus beta is less than alpha plus gamma. So it's obvious from the definition of plus in R that alpha plus beta is a subset of alpha plus gamma. That's just obvious because this is all the elements of alpha plus all the elements of beta. This is all the elements of alpha plus all the elements of gamma. And we're given that beta is less than gamma and alpha is the same. So these have to either be the same or less than. So we just need to show that the two sets cannot be equal though, because if alpha plus beta equals alpha plus gamma, then the cancellation law, which is 114a, implies that beta equals gamma. But we started by saying that beta is less than gamma, so that's a contradiction. So they can't be equal. We know that they're either less than or equal, so they must be, so alpha plus beta must be a proper subset of alpha plus gamma, which means that alpha plus beta is less than alpha plus gamma. So the last thing we need is one of the properties that comes from the ordering, the important one, that if x is greater than 0, then minus x is less than 0. Okay, so if we start with x is greater than 0, then that implies that x plus minus x is greater than 0 plus minus x, right? This is one of those things that we should just know how to do. So x plus minus x is 0, and 0 plus minus x is minus x. That's it. Okay, so therefore minus x is less than 0. Okay, those are the things that we're going to need to verify the multiplication for negative numbers. Okay, so with that in hand, we're going to define, what we have to do is, so far we've defined multiplication if alpha is greater than 0 and beta is greater than 0. So using this, using our definition of this, we're just going to define what it means if one of these or both of them are less than 0. So first of all, we're going to say, we're just going to set that alpha times 0 equals 0 times alpha equals 0. Okay? Now, that's just setting, we set that, and then we set, so we're basically just defining alpha beta for negative numbers. So alpha beta equals minus alpha times minus beta if alpha less than 0, beta less than 0. Whoops, I went up at an angle. It equals minus alpha beta if alpha is less than 0 and beta is greater than 0. And the opposite, it equals minus alpha times minus beta if alpha is greater than 0 and beta is less than 0. Okay, those are the three possibilities. And in each case, now we're just defining what it means to multiply alpha times beta. If they're both negative, then you just take the opposite of both of them, and that's what that equals. Or it's the opposite of multiplying the opposite. And you can see that the reason this works is that each one of these is multiplying two positive numbers, which we already know how to do. So here, and that's why 118 is important, that if, and this is vice versa also. So if alpha is less than 0, then the inverse of alpha will be positive. So these are both positive. We know how to do that. Here, this one's positive. So these two are positive. We know how to do that. And then we take the additive inverse of that. That's what alpha beta means in that case. And then the same thing here. If beta is negative, then you take the opposite of that one. Okay, so we've got to show that these satisfy the multiplication axioms as well. Basically, all we have to do is use the rule that gamma equals minus gamma. We do this over and over, and then that should prove everything. So we're just going to go through our the 5 axioms. So M1 is closure. And this doesn't really need proving, because closure just means that alpha beta is going to be a cut if either one of them are negative. And so if alpha is less than 0, then we know that minus alpha is greater than 0. That's 118a. And that means that minus alpha times beta is already defined because these are both positive. And that's the definition. Alpha beta, if alpha is less than 0, equals minus alpha times beta, which we know is defined. So, and we know that it's closed. So the closure is automatic. If they were both negative, then if beta is -2, then beta is going to be, then negative beta is greater than 0. So both the definition of alpha beta, if this is positive and this is negative, would be the same. Or if they're both negative, then it's minus alpha minus beta. We know from 118a that this is positive, this is defined, so that's it. That's all there is to closure. So M2 is commutativity. So again, this is also very obvious. So we're just showing that need to show that alpha beta equals beta alpha. Well, say that alpha is negative. That means that alpha beta equals minus alpha beta. That's the definition. And then these are both positive. We know, again, with positive multiplication that this is commutative, so we can just rewrite that. Minus beta. And that's the definition of multiplication when the second multiplicand is negative. So that just equals beta alpha. That's it. And if they're both negative, then it's just, negative alpha, negative beta. Those are both positive, so you can rearrange them, obviously, and then you get equals beta alpha. So that's also easy. Now, associativity is a little more involved. Let me go to the next page, because we're going to have to prove a couple of different possibilities for this. So, M3, associativity, we need to show that, of course, alpha beta times gamma equals alpha times beta gamma, right? But we're going to have to show it when one of them's negative, when two of them are negative, or when they're all three negative. So, and if we do that, if we show that alpha is negative and then alpha beta is negative and then all three of them are negative, the rest of the permutations will be just, you could rearrange them to begin with to fit the definition that we want. So, right, because if, let's say beta is negative and alpha is positive, then we just showed that it's commutative, so we could just rearrange them. Beta alpha gamma will then equal beta times alpha gamma. So we just have to do the three cases. So if alpha is less than 0 and beta gamma greater than 0, so alpha beta equals, once again, minus alpha beta minus. But we know, since these are both positive, that this whole thing is positive. So minus alpha times beta is greater than 0. That means that if you take the opposite of the whole thing, is less than 0. Okay? So we have that this is negative. So alpha beta is less than 0. So now if we look at the whole thing, we have that alpha beta gamma equals. So now we have a negative. We just showed that this is negative. So we have a negative times a positive equals negative. Now this gets very involved. I have to be sure that I get it right. So it's the negative of this times gamma. Now I'm going to rewrite this using the definition of a negative times a positive. So this might not have been even necessary, because now I'm going to do minus, rewrite this. So we have inside here, we have minus alpha beta. And then another in parentheses, and then gamma. Okay, so what I did is I just replaced this with its definition, which is this. The rest of it's the same. Okay. Now, using the rule that gamma equals minus gamma, we can take away two of these, and then inside, it's this times this. So we can get rid of these two. So this equals minus gamma. Okay? Now what we have inside of the square brackets, we have a positive, and a positive. And these two are around parentheses and that one's not. We know when we're all positive that we can use that these are associative. So we can do minus, and then we can move the parentheses here. So we have minus alpha, and then beta gamma. Okay, just switch the parentheses. This then is the definition of alpha times beta gamma when alpha is negative and this is positive. And we know this is positive because beta and gamma are both positive. So that's it. So we showed that for when one of them is negative and the other two are positive. So let's just keep going. So when alpha is less than 0 and beta is less than 0 and gamma is greater than 0, then we have alpha beta gamma equals. So now these are both negative, so that means that this is minus alpha minus beta gamma. Now these three are all positive, so we can switch the parentheses again, and we have minus alpha minus beta gamma. Oh, this whole thing now is positive. So I'm going to use 114D. So rewrite this by adding two minuses here. So we have minus A, minus alpha, parentheses, and then minus, and then all of it. That's that one. Square. Okay. Now, what did we accomplish here? This in here is the definition of a minus times a positive. So we can rewrite this using what this is defining. So we have that it equals minus alpha, and then we still have this one, but then what's inside here is minus the opposite of beta times gamma. That, in other words, is, right? Because beta is negative, gamma is positive. The definition of that is this right in here. That is beta gamma. And then we took the inverse of that whole thing is here and then multiplied it by minus alpha. Now what do we have? This is negative. That makes this positive. Well, so this is negative and alpha is negative. So this whole thing's negative, this is negative. That means that this is the definition of two negative numbers multiplied. So we have that this is alpha times beta gamma. And that's what we wanted to prove. Okay, good. Just one more to go through. When alpha, beta, gamma are all less than 0. So we have that alpha, beta, gamma equals, and so we redefine this, negative, negative, so that's minus alpha minus beta times gamma. That's just the definition. Now, these are both positive. That means that this is positive and this is still a negative. So we can rewrite this as the definition of a negative, of a positive times a negative. So we have minus, and then we're leaving the first one. So that's minus alpha minus beta times the opposite of gamma. So now this is positive and these are positive. So once again, we can use associativity. So this equals minus, take out the alpha and then switch the parentheses here. So we have minus beta minus gamma. Okay. Now these are both, this is the definition of the multiplication of two negative numbers. So we have minus alpha times beta gamma. So we're almost there. And what do we have here? This is the definition of a negative times a positive. So we can rewrite that as alpha times beta gamma. Okay, we did it. So next, M4 is multiplicative identity. So we need to show that alpha times 1 equals 1 times, alpha times 1 equals alpha when alpha is less than 0. Now notice for this one's easier than associativity because we're only dealing with one number. We already know that if alpha is positive, that works. So alpha times 1 equals, this is just rewrite it as the definition. And then that equals just the identity. This is a positive number, so we know that the identity works there. So we have minus. And now using the rule again, 114D, we have that this equals alpha. And that's it. For the last of the multiplication axioms, it's multiplicative inverses. We need to show that there exists beta such that alpha beta equals 1 when alpha is less than 0. Again, we're only looking at one element here. We don't know, we don't care whether beta is positive or negative. That's what we're looking for. We just need to know that that one exists that will make this positive. Of course, we know that this is also going to be negative, but we just have to show that one exists. So let beta be the inverse, multiplicative inverse of minus alpha. Now alpha is negative, so minus alpha is greater than 0. So we're going to take this, so beta here is actually, let me just use a different, let me say gamma here. Okay, so we're going to let gamma equal the inverse for minus alpha, okay? So we know that exists. We've already shown that because they're both positive. Then 1 equals minus alpha beta, or minus alpha gamma. That's the definition of gamma. So we have that 1 equals minus alpha, so that's positive, and this is positive. So now we're going to use the reverse definition here. What happened to my pen? What did I do? It's weird. Okay. We're going to reverse the definition of this. So this, the positive of this equals the negative, oops, times gamma. So the inverse of minus alpha is negative, and the inverse of gamma is negative. So negative times a negative is defined as just the inverse of both of them, right? Okay, so now we can apply our rule to this to come up with alpha equals minus gamma, or alpha times minus gamma equals 1. And that's what we needed to know. So let beta equal minus gamma, and we're done. All right. Okay, so that's it. We've proven all of the multiplication axioms for all of the real numbers, negative and positive. We have one last thing to do for the field axioms, which is distributivity. Now, because it's multiplication, this gets to be, because it involves multiplication, this gets to be a little bit annoying as well. But we need to show that alpha times beta plus gamma equals alpha beta plus alpha gamma, right? So this proof, we just have to, like we did with associativity, we have to break it into cases. The first thing we have to show is if they're all positive. This requires an actual proof, and then the rest of it is going to be easier after that. So first, all positive. So beta plus gamma is defined as the set of all s plus t, where s is an element of beta and t is an element of gamma. So beta plus gamma is a cut made up of all of the elements s plus t. So now using multiplication, alpha times beta plus gamma. So beta plus gamma is a set, is a cut consisting of all of the s plus t's. So alpha times beta plus gamma is defined as the set of all p less than or equal to r times s plus t, where r is an element of alpha, and then s plus t is beta plus gamma. Okay, so this is the definition of multiplication. It's all the p's less than r times s plus t. So p less than or equal to r times s plus t implies that p is less than or equal to rs plus rt. So then alpha beta is the set of all u such that u is less than or equal to rs, and alpha gamma is the set of v such that v is less than rt. So then alpha beta plus alpha gamma is the set of all u plus v such that u plus v is less than or equal to rs plus rt. So we already showed that p is less than r times s plus t, and we have that u plus v is rs plus rt. That means that p and u plus v are the same. So we have that alpha times beta plus gamma equals alpha beta plus alpha gamma. That's for positive numbers. So the remaining cases, if one of the numbers is negative, then it all works the same way. And I'll just show you, for example, let's say that alpha is greater than 0, beta is less than 0, and beta plus gamma is greater than 0. Then gamma equals beta plus gamma minus beta. And now, so we know then that the distributive property will hold for these because they're all positive. So we can multiply both sides of the equation by alpha. So we have that alpha gamma equals alpha times this whole thing, beta plus gamma minus beta. So we can distribute the alpha through this. We couldn't do that without what we just did with the distributivity property for positives. But we know that it holds now, so now we can distribute this through. So alpha, beta plus gamma minus, or plus alpha times minus beta. Okay, but alpha times minus beta equals minus alpha beta. That's because alpha beta equals minus alpha times minus beta. Therefore, this is the uniqueness of the inverse, which is 114c, which was the other one that we needed. So if these are equal, then their inverses have to be equal too. Now again, we can use our rule again, get rid of the two minuses, and we end up with alpha times minus beta. So now going back up here, we can take this one and add alpha beta to both sides. So we have alpha beta plus alpha gamma equals alpha times beta plus gamma plus alpha times minus beta plus alpha beta. We just showed that alpha beta is the inverse of this, so these two cancel, and we're left with alpha beta plus alpha gamma equals alpha times beta plus gamma. Okay, so that shows it for these conditions, and then you can just do the same thing going through for all the different minuses. I'm not going to do the rest of them. That's it. We're done with multiplication now. We've shown that the cuts have the least upper bound property, and we've shown that they have the that they're a field. We still have to show that they're an ordered field, and then we will have what we wanted all along, which is an ordered field with the least upper bound property.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.